It's worth noting now that the simple oscillations we've seen so far are, while common and useful, they can be generalized one step further, and those generalizations show up everywhere in other sciences, especially physical sciences. Let me show you what I'm talking about. When we had this shifted, scaled, horizontally shifted form, the B factor, the multiplier of the cosine or sine, is the factor that sets the amplitude. And we've treated that as a constant, like a single number in previous examples. However, there's no reason why we have to do that. Let's do a quick comparison here and talk about what this B value can do if it's not constant. We'll start with a constant, 5, and we'll recognize that if that's 5 and that's minus 5, that we'll talk about a cosine graph that looks like, sketched out like so. This would be the graph of the cosine. And let's take that 5 and ask ourselves, what's the graph of absolute value of 5, or y equals 5 and y equals negative 5? That graph would be these two horizontal lines. Y equals 5, y equals negative 5. And in some sense, or very real sense, those are boundaries for our cosine graph. Why are they boundaries? Well, because cos is never greater than 1. So the biggest, when we look at cos times 5, the biggest we can ever get is going to be 5. And because the smallest cosine ever gets is negative 1, we can always bound our graph of 5 cos x between 5 and negative 5, those nice simple values. But what if we trade in this 5 for something a little more interesting? Okay, what if we trade that 5 in for the function x, not constant? Well, what can we say about this? Let's say we have cos of pi x, and we multiply it by x out front. Well, because this is always less than 1, less than or equal to 1, x cos of pi x will always be less than x, and because this is always bigger than or equal to negative 1, it'll always be larger than negative x. Okay, what does that get us? Well, y equals x is, we won't do it quite to scale here. Let's go here. 1, 2, 1, 2, 3. If we were to scale this cosine function, let's draw the graph of y equals, let's draw the graph of y equals x, look like that. And the graph of y equals negative x, which would look like that. The graph of cos of pi x will oscillate between those two functions. Going to go back one slide. The graph of y equals 5 and y equals negative 5 was the boundary for 5 cos of x. The graph of y equals x and the graph of y equals negative x is going to be the boundary for x cos of pi x. Let's see how that works out. Make a quick note about the period. We put this pi in here to make the period nice. The period would be 2 pi divided by the multiplier, so a period of 2. And cos of pi x is going to equal 0 at, well, the half cycle. So remember, cos goes up then down. That'll be at x equals a half, x equals 3 halves, x equals 5 halves, etc. Because that cos of pi over 2 is 0, cos of 3 pi over 2 is 0, and so on. So we have some landmarks here. Okay. Now, our challenge is to sketch the graph of cos of pi x with this period. We know the period, but we know it's going to oscillate in between these two boundary levels. In particular, it's going to reach the boundary level at Here we go. It's going to reach the boundary on the bottom at 1, and then it's going to go back to 0. And then it's going to reach the boundary again at 2. And then let's go back to 0. And you can see what we get here. We get oscillations whose amplitudes are increasing as we move from left to right. And so there's lots of sound type of things or physics models where this kind of oscillation appears. And this is how we'd model it. We would say we'll have an oscillation, a cosine, but the amplitude will not be a constant. It'll be some other function. And it really broadens what we can do with our cosine sine functions. For those taking differential equations as a later course in second year, this kind of pattern emerges as a very important feature of physical models. All right, let's try extending that one more time, again with a non-constant multiplier or a non-constant amplitude. And this time we'll do it a little more quickly. Again, we choose cos of pi x because it gives us a period of 2 pi over pi, or just 2. So nice integer cycles. And let's do it like so. I won't really give a vertical axis here. We won't go into the details of that, but we'll sketch out our classic exponential function. So our classic exponential function looks like this. And then it also has a mirror image, the negative version. So this would be e to the negative x and e to the x. Sorry, this is negative e to the x. Let's get our shifts correct here. There we go. And what we see when we take the cosine and use this as a boundary is that the cosine will start at its peak at the half marks. It'll be at 0, then it'll reach the bottom half, top, 0, bottom, 0, top, 0, bottom, 0, and then we're done. So we will see oscillations that look like this. Oops, gotta get back down fast. Again, we can see the fundamental oscillations here, but the amplitudes vary dramatically and very dramatically as we increase x here. And it's just a much more interesting shape to work with. And again, one that is seen in nature more often than you might expect initially. So that's an introduction to how we can use non-constant amplitudes. And if you start thinking about derivatives, if we're asking about rates of change of this, you can see a classic example of where we would need both a product rule for multiplying these two functions, as well as the chain rule for handling these scalings and shiftings inside the cosine function. So this is probably new for most students. If it's unfamiliar, take a look back at the examples and see if you can get your mind around this idea of a varying amplitude for oscillating cosine sine functions.